Hi, my name is Josh Garrick, and I'm participating in Challenge 2010. Today I'll be speaking to you briefly about limits and continuity and the topics of differentiability all surrounding the same topic. So I guess the first thing I really want to do is share with you the definition or what the book has to say about limits to give you a little bit of insight into what I'll be talking about. So here we go. The limit process, an intuitive introduction. So we could begin by saying that limits are important in calculus. Let me see if I can get this better. We could begin by saying that limits are important to calculus, but that would be a major understatement, because without limits, calculus would not exist. Every single notion of calculus is a limit in one sense or another. For example, looking at the bottom of a page, what is the slope of a curve? It's just the limit of slopes of secant lines. What is the length of a curve? It's the limit of lengths of polygonal paths inscribed on the curve. What is the area of region bounded by a curve? It's the limit of the sum of areas of approximating rectangles. And as you can see in the figure 2.1.3, here are pictures of these three examples that I just read off to you. Yep, so limits. Again, the basic idea of a limit is there are technically several limit processes, but they are all very similar. And once you master one of them, the others will pose very few difficulties. The limit process that we start with is one that leads to the notion of continuity and the notion of differentiability, which is pretty much just whether a graph is continuous on a line or whether it's got holes going from one place to another. So I guess really it's just easier to start with an example on limits and continuity, so we'll start with this. So yes, it's all written out and worked out for you on this, but disregard some of that for a second and let me walk you through what's going on here. So in our first example on, I guess, this side right here, we see that the limit as x approaches 2, which is how it is written here, the limit as x approaches 2 of x squared does in fact equal 4. But the way that we can see that is graphically. On the graph, you see the graph of x squared is the parabola. And we see that as the graph is approaching x squared, as the graph is approaching 2, this point 2 here on the x-axis, we see that it will line up with the point 4. And that's as x is approaching 2 from both sides, you can see that. You can see the arrows pointing from both sides. But you're saying, yes, you could just plug in the value 2 squared equals 4. But that's not always the case, as we can see in this example on the other side, where we have f of x equals the same graph x squared if x does not equal 2. While if x equals 2, then f of x equals 3. So we see here, we don't know exactly what it would be at first covering up our answer, but we can look at the graph and see that the same graph x squared, we can see that it is approaching the same point on the graph. Yes, it is approaching 4. As x is approaching 2, it's approaching 4. So we see that there's a hole in the graph because it's when x does not equal 2, f of x equals x squared. But when x equals 2, f of x is actually 3, which makes the graph continuous. And though the limit is still 4 because as you're approaching it from both sides, you're still approaching the same point, f of 2 is not 4. As you can see, f of 2 is 3. So pretty much this is just to prove the point that yes, it can be continuous and discontinuous, while it is also not always the same. Saying that f of x is not always f of 2. You cannot just plug the value into the equation to get an answer. I guess what would help make it more clear is another example. So Let me show you another example of this limit process in continuity. So we have the limit as x approaches -1 of 2x plus 2 over x plus 1. Yes, we see that the answer is 2, but we see that when you plug in -1 into the equation up here, we see that you come out with 0 over 0, which is actually undefined, so you can't use that. But working it out, we see that the f of x value is actually equal to 2 times, we all know, factoring out the 2 on the top, you get 2 times x plus 1 over x plus 1. So the x plus 1's can cancel, and f of x equals 2. But with that, we also know that it can't be at -1. So f of x equals 2 when x is not equal to -1. And it is undefined at -1. As we can see, there's a hole in the graph at -1, but everywhere else it is continuous. Well, the graph itself is discontinuous, but x still equals 2. To check yourself, you can test the values by saying f of points very close to -1, such as -1.0001 or -0.999. We can check ourselves and see that this is still the limit because the values are still all approaching -1 from this graph of 2x plus 2 over x plus 1, and the answer would still be 2. So this is really just a brief introduction, but it's trying to give you a little bit of information, a little bit of insight into what limits are and how you can go forth in calculus or whatever math you're going into with the limit process and all that. So hope it helps.